All right, so this video is going to run through the free body diagrams and net force equations for something called a half Atwood machine. So an Atwood machine is something that allows us to lift heavy objects without having to apply as much force as however much the object weighs. So it allows us to kind of indirectly pick up the object. So the first half Atwood machine we're going to look at, it's called a half Atwood machine because we are half on the table, half hanging, is when the Atwood machine is accelerated via an applied force. So I have this force F here, and I have this mass M1 here. Okay? So the only object in my system is M1, so I really only need to draw one free body diagram. So M1 has a force of gravity, which I could calculate by doing M1 times G, and we have a normal force. M1 also has a tension force acting on it. Now, this string is all the same string. Okay? And essentially, in this string that I'm pulling on with a force F, there's a bunch of Newton's third law pairs as we travel up the string. And what that ends up happening, or what ends up happening, is that this tension force is exactly equal to the applied force. Okay? So my net force equations here, in the y direction for M1, would be 0, as I'm not accelerating off the table or crashing through it. So I would FFN minus M1G, 0, and that just tells me my normal force has to equal the weight or the force of gravity. And in the x direction, I'm going to accelerate. So the thing that is causing that acceleration of my net force is the tension force, which we talked about is equal to the applied force. So M1A. Not really much different from kind of our standard objects. Where things can get a little bit trickier is when the accelerating force comes from not an applied force, but a hanging mass. So now I have two objects in my system. So I have a couple of different options for how I want to define my system. I could think of M1 and M2 individually, or I could think of the M1 plus M2 system. So on M1, I'm going to have a force of gravity and a normal force. And then I have that tension force, right? And this mu k equals 0 just means it's a frictionless surface. And then on M2, I'm going to have an M2G and a tension force. Kind of like what we described above, there's a bunch of Newton's third law reactions going on in between that string. So this tension force and this tension force are the same. Okay? Now you'll notice I drew my tension force less than that FG2, my force of gravity here. That's because this system is going to accelerate downwards. That's kind of the only option for this. So what that means is that this downward force has to be larger than this upward force, so I have a net force downwards. Now what gets sort of confusing about this sort of system is that I have one object moving to the right and one object moving down. So I have objects moving in different directions, so like my net force equation in the x and y direction here is going to be like, because I'm accelerating in the y direction here, but x direction here and x and y direction aren't supposed to mix, so things get a little bit confusing. So what I usually recommend doing is rotating one of our free body diagrams so that it makes it seem that everything's accelerating in the same direction. And I usually rotate the free body diagram of the hanging mass. And I'm going to pretend that instead of this accelerating down and this accelerating to the left, or sorry, to the right, that everything is just accelerating to the right. And I'm also going to make to the right positive. Okay. That makes it so my net force equation in the accelerating direction for M1 looks like Ft is M1A, and then my net force equation for block 2 looks like M2G minus Ft is M2A. Again, where this force and this force are the same. Now there's still a net force in that sort of y direction for the first mass. That shows us that the normal force equals M1G. That one hasn't changed at all. Okay. So this rotating the free body diagram, and we're always going to have tensions pointing towards each other. kind of makes it really easy for me to see that, okay, this tension comes from this tension, which comes from this force of gravity. And it kind of lets me see that, okay, if this tension is less than the force of gravity, then this tension is also less than the force of gravity. It kind of lets me see some comparisons a little bit better. It also helps me better draw my free body diagram for the two object system as a whole. Okay? Because once I have everything rotated, and once I'm talking about the two objects as a whole, the thing I have to keep in mind is that that tension force, because it is between my two objects, like an interaction between my two objects, my tension force is now internal. So the only other external forces we have, kind of leftover forces, is I have the force of gravity and the normal force acting on M1, and then since all the tension goes away, I just have an M2G. Okay? So my net force equation for the system, two object system, that is the accelerating net force, is going to look like M2G. So the force of gravity on this is what's causing the system to accelerate. And I have the total mass of the system times the acceleration, where the acceleration is the same. And then, of course, still have that the normal force equals M1G. That hasn't changed. Okay. So what this allows me to see is that my force of gravity is really what's causing the system acceleration, and that force of gravity will help determine my tension. But I know that the tension force has to be less than the force of gravity. Okay. Now, there is a question in our workbook that kind of compares this system to this system, where this applied force and the downward force of gravity on block 2 are the same, and it asked us to compare the tension forces first and then also the acceleration. So that's an interesting question to look at. The last thing we're going to pay attention to in this this sort of video is the friction force. Okay? So friction's only going to impact M1. Okay? Now, the thing to keep in mind is that the direction of friction depends on our direction of motion. So it's important to pay attention to what direction is my object moving, because the direction of friction is going to change whether I'm moving to the right or moving to the left. So let's say I am moving leftward. Okay? Friction is always going to point opposite the direction of motion. So if I'm moving left, then that means friction has to point to the right, along with tension. Whereas if I'm moving to the right, friction, M1G, Fn1, friction, has to point to the left. Okay. So this is going to kind of change up my net force equations. Here, friction and tension add together, whereas here, friction and tension are subtracting each other. So that's going to give us some sort of ideas about how the net force might change based on whether we're moving left and moving right, and also how the acceleration might change for moving left versus moving right. So to think about that net force and the acceleration, let's look at the total system, so the M1 plus M2 system. Okay. Remember, I can rotate this M2 to kind of better give me an idea of how to draw that. So once again, if I'm doing the M1 and M2 system, the tension forces are now internal. Now, even though the force of friction is like between the two blocks, as in like direction, friction is really a force between M1 and the surface. So when I say between the two blocks, I mean like an interaction between the two blocks, not like physically in between them. So this system, again, is going to depend on whether we are moving left or whether we are moving right. My normal force, oops, wrong direction. My force of gravity and my normal force are not going to change whether I'm moving left or moving right. That's going to stay exactly the same. G1 and 1. What does change? Oh, and M2G doesn't change, right? We're not changing gravity. What does change is the direction of friction. So if I'm moving left, the force of friction has to point to the right. And if I'm moving right, the force of friction has to point to the left. Now these values of force of friction are going to be the same because we calculate that force of friction. We're doing mu k times the normal force. We're not changing the normal force. We're not changing the surface. So, whoops. So these values are the same, just in different directions. So what this is showing me is that this free body diagram is going to end up with the greater net force and therefore the greater acceleration, because these two forces point in the same direction, whereas these two point in opposite directions. That's kind of a brief overview of the half Atwood machine.